If you drop a solid steel bolt into a bucket of water, it instantly plunges to the bottom. Steel is about 8 times denser than water, so gravity wins the fight without hesitation. Yet, giant container ships, built from thousands of tons of that exact same steel and loaded with thousands of heavy metal cargo boxes, float across deep oceans with effortless grace. It looks like a contradiction, but it is actually a precise application of fundamental physics. To understand why a massive metal ship stays afloat, you have to look past the raw material and focus on average density and displaced volume. Density is simply how much mass is packed into a given space. If an object is denser than water, it sinks. If it is less dense overall, it floats. A solid block of steel sinks because every cubic centimeter of it contains heavy iron atoms with no extra space. But a ship is not a solid block of steel. It is a massive hollow shell filled mostly with empty air. Air is incredibly light, roughly 800 times less dense than liquid water. When shipbuilders shape steel into a wide, deep hull, they are enclosing a gigantic volume of air inside a relatively thin skin of metal. The overall density of the ship isn't just the density of the steel. It is the total mass of the steel, cargo, fuel, and air divided by the entire volume of the outer hull. Because air takes up almost all of that interior space, the ship's average density drops dramatically, ending up lower than the density of the surrounding ocean. This balance is governed by Archimedes' Principle, which states that any object placed in a fluid experiences an upward buoyant force equal to the weight of the fluid it pushes out of the way. Think of water as a crowded room. When a hull enters the sea, it pushes water out of its path to make room for itself. That displaced water wants to push back and return to its original position, creating an upward force against the bottom and sides of the hull. Imagine taking a piece of aluminum foil and rolling it into a tight, solid pebble. If you drop it into a bowl of water, it sinks right down. But if you take an identical piece of aluminum foil with the exact same weight and fold it into a wide, shallow boat, it floats easily. You haven't changed the mass of the metal, but you have vastly increased the volume of space it occupies in the water. The boat shape pushes aside a volume of water whose weight easily equals the weight of the foil before the boat goes under. For a cargo ship, the math works the same way on a colossal scale. As the ship is lowered into the ocean, it sinks deeper and deeper into the water. As it submerges, it displaces more and more water, which increases the upward buoyant force. The ship stops sinking the exact moment the upward force from the displaced water equals the total downward force of gravity pulling on the ship and everything inside it. At that precise depth, known as the draft line, the forces are perfectly balanced and the ship floats happily. When heavy cargo is loaded onto the deck at a port, the total weight of the ship increases, pulling it lower into the water. As the hull settles further down, it displaces an extra volume of water equal to the weight of that new cargo, raising the upward buoyant force until a new balance is reached. If the ship unloads its cargo, it becomes lighter. The displaced water pushes it upward, and the ship sits higher in the water. Staying afloat, however, is only half the battle. A ship also has to stay upright. If all that displaced water pushes up in the wrong place, or if heavy cargo shifts to one side, a vessel can capsize. Engineers carefully manage the center of gravity, where the downward pull of weight is concentrated, and the center of buoyancy, where the upward lift of displaced water acts. By keeping heavy machinery low in the hull and using liquid water ballast tanks to adjust weight distribution as cargo changes, ships remain stable even in rolling storm waves. Ultimately, a steel ship floating on the ocean is a triumph of geometry over raw material properties. By taking a heavy, dense metal and stretching it into a vast hollow structure, human engineering traps enough low-density air to trick the water into supporting thousands of tons of steel. It isn't a miracle or a defiance of nature, but a perfect harmony between shape, mass, and the weight of displaced water.